first things you do in network analysis is visualize your data as best you can, because it really does help give this sense of a holistic feeling. So what I want to do is give you some sense of ways to do it that's smart, as opposed to ways to do it that are not as smart. And network data has been, network analysis has been a visual field for a long time. Ever since the beginning of the field, it's really been this sense in which using network diagrams makes things that are impossible to see just intuitively really clear and crisp, or at least ideally. So, let's see if we can get this to work. There we go. So I'm not going to do all of this today, so we'll just start at the beginning, just in the interest of time. The first network idea came from Wheeler's treatment of the classic problem of the 7 bridges of Knigsberg. People know this little mathematical problem? The problem is, what you'd like to do is be able to find a way to cross between these 7 bridges once, but only once, and never repeat, right? And so could you do that or not? And this was a mathematical problem from 1741. And it's a really easy problem to do if your bridges are arranged on a single line. You just go right to left, and you could easily cross each bridge once and never cross another bridge twice. But if you needed to do it with an island in the middle and these 7 bridges, how is it possible? And the trick that he came up with to solve this problem was the invention of graph theory. And so you abstract from the island and bridges to an island and edges. In this case, it's a multigraph. And it turns out that you can't possibly get to this spot without going over 2 simultaneously. And so this was part of the original instinct behind network analysis and network modeling, and the idea of a graph for representing something that's as an abstraction of something that's real. The other abstraction you're probably familiar with from an original network idea is a kinship diagram. So you have these are some early work done by Morgan to look at great-grandparents, grandparents, parents, and children, for example. And this is a classic study. The other example you're probably used to seeing is something like a bureaucratic chart, right? So in this case, you have I think this is a German bureaucracy. It looks a little bit like Duke. I've tried for years to get the Duke organizational chart, and they won't give it to me. I think they're afraid of what it might reveal. But the actual sort of kickoff to social network analysis are Jacob Moreno's work in Who Shall Survive. And what he started with was this idea of trying to map the relations amongst kids, and with the thinking that it might be possible to reveal something that you wouldn't see otherwise. And so, for example, he developed this idea that positive ties were in red and negative ties were in black, and reciprocal ties have this little hash mark on them. And you can see amongst this classroom, there's one girl, CM here, who is disliked by everyone else in the network, right? So it's really clear from this case that CM's, and not only that, but CM's one close friend is a friend with somebody who hates her, right? So this was the idea that Moreno had, that it was really easy once you saw this to realize that whatever's going on with this is structuring everything else that's going on in this classroom. And if we can solve this problem, we might be able to do something overall in this setting. And so it was this kind of idea. And he was also one of the first to recognize, in this graphical sense, the difference between boys and girls and the fact that they didn't have relations between each other. I showed you this map the first day. In this case, these were runaways that were being held in a sort of a hospital-like setting in New York in the 30s. And they lived in these little camps, these little cabins. And there were friendships within and between. And this was actually a three-colored, multicolored relationships to look at friendships and hate and so forth. But there were a bunch of kids that were not tied to each other. But the idea was that if you could look at these maps, you could understand something about the world that you wouldn't see otherwise. And the kinds of maps that people were drawing were really ad hoc. They were just trying to figure out something that was intellectually pleasing, with the idea that you would have a few elements that you could trace through the relations. And so they really worked hard to make it possible to move, for example, in this work, these were different plates across a book, that if you started on this plate and followed this line over and came up to this side, you could actually trace it again. And so all of these diagrams were linked, all done by hand, right? All done by hand without any kind of computer assistance. This was just done by drawing it as best they could and redrawing it again. I love things like this, which we now would call a swim lane, where you take lots of ties that come into one person, putting into one, and so forth. The early conventions that developed was the idea to use size to represent some kind of prominence in the network. So in this case, these are households, and this is a very prominent household, and you can see it by the number of ties coming into it. As time went on, people thought it would be a good idea to layer more information over the network. And so this is an early example of using a pie chart to distinguish something about, in this case, the distribution of visits within and between family members. In this case, about 3/4 of the visits to this household were from family members versus between family members. But again, the layout in this set is entirely done by hand and just to the artistic eye of the investigator. The first attempt to come up with something more than a simple artistic eye sort of approach was Nottingham's what were called target sociograms. This is very similar to the heuristic that Network Canvas uses, which is that there's some measure of prominence, a centrality measure, that you put those folks at the middle and peripheral folks to the outside, and you'd have some kind of a scaling on one side or the other. In this version of it, they distinguish between females on one side and males on the other. If you don't like circles and triangles, you could use little faces with bows in their hair and little faces without bows in their hair, right? And so the idea would be that this is a very central girl, and this is a less central girl, and this is a less central boy, and so forth. This is the algorithm they use for that layout. It's a pegboard rubber bands. There's actually a 3D version of this where they stacked up a series of abaci, and used that to string rubber bands. But it was literally, you would put it in the pegboard and you'd move it around until you minimized the edge crossings. Some of the current software will do this, so PAYAC will do this for you now if you want, without the rubber bands. The idea that there might be some sort of a metric arrangement to ties, of course, brings people to the classic idea of using something like a scatter plot. And so in this case, the y-axis is a socioeconomic scale, and the x-axis was used to try to arrange friendship groups that had more ties with each other. This quickly fails. It just becomes miserable. And part of the reason is that there's never a complete one-to-one correspondence between some metric like an SES scale and patterns of relations, even in cases where there's high distinctions. People have tried other things, right? So there's a polar coordinate version of this. This is done by Joel Levine in the 70s to look at interactions between organizations. It's actually not a bad graph if you get rid of the really ugly grid underneath it. There's actually more information there than the display works. Computer ideas have gone on since then, and so this is a map of the internet that was done in the mid-2000s. And this is kind of fun because it's what's known as a hypersphere. So as you zoom in, the sphere sort of moves on the outside. You can move through it. It's a really great way to explore trees, but it's not very good for social networks. But the idea of having these kinds of visualizations and the popularity of networks has led from some sort of scientific sort of move of thinking about visualizations to a lot of things that have gotten a little silly. So this is an example of an ad campaign for hand lotion, where the idea is that this person tells all her friends, who tells their friends, and so forth down the chain. The New York Times has picked up on these, right? So this is an example of bankers in New York or politicians in New York. And even worse, this is the military's assessment of the elements that are driving the problems in Afghanistan. Right, so if this is your causal network model, you wonder why you would not want to work there. There are even, of course, some spoofs, so actual scientific research, right? So do your friends make you fat? After the Christakis study that came out, this was an editorial that showed up in one of the newspapers. And lest you think that just newspapers and media folks get bad visualizations wrong, this was published, this is a classic hairball published in Real Science. And that's the real problem, right? So the problem that we have in front of us is we would like to find a way to use these visualizations to build some intuition and do something intuitive that's nice, that lets us see the world in a nice way, without coming up with something that looks as ugly as this. And so that's the challenge we have before us. And so if we literally want to get to the point of where we make the invisible thing visible, we need a telescope. We need some way to see it. And so if seeing is believing, then we'd like to have, kind of like Galileo, to have our favorite little telescope. But the problem is that the way you look at things really depends on what you see. And so there's a lot of visual tricks that you want to play with, whether or not you see a young woman or an old woman, whether or not you see the water moving up or down, for example, is a classic bit. And so what we need are some guidelines for how you do visualizations to try to get rid of some of those visualization problems and do it nice. And so I have sort of a couple of basic things that I want to sort of try to harp on. The first is some basic quantitative visualization craft. And for those of you that haven't gone out and bought every one of Tufte's books and have it on your bookshelf and read it before you go to bed every night, I highly recommend you do so. That's the way, Tufte's work on the clarity of visual design for quantitative work is probably the best out there. And the key idea there is that you focus on clarity, scaling, the avoidance of chart junk and so forth to make things as clear and information-laden as possible. I'm not going to spend a lot of time talking about that today, but the main distinction there is to try to move between things that are clunky and ugly to things that are elegant and beautiful. And you do that with things like line weightings and colors and so forth. And it's the same information with just a little bit of a tweak. What I want to focus on more today are the elements of network-specific graph display as opposed to general quantitative display. And networks, the main element here is that networks represent a social space. And the idea behind a good network visualization is you somehow capture that space. And what that space actually is, of course, is a little hard to know. And we can have a two-dimensional version of social space, a three-dimensional version of social space. It turns out that a social network, to represent it perfectly, requires n-1 dimensions, which you can't visualize. So the real problem of visualizing social networks as this analogy of a social space is you want to do it in a way that gets it down to 1 or 2 or 3 dimensions, but does it in a way that doesn't do as much violence as possible to the real dimensions that are out there in the set. So you want a heuristic that does that in a clear and nice way. So how do you do it? There are a couple of ways that we're going to play with. I'm going to skip that one for now. The idea is that we can work through models for social space. The kinds of ideas we want to play with are things about have to do with the resolution. So do we care about a global level versus a local level? And what kind of attributes do we want to play with? The rubric I'm going to work with is this notion between a visualization strategy, the question you want to answer, and the scientific problem of data fidelity. All right. So let's start first with what we're trying to do, right? So what makes a good visualization? We want to help build intuition about the social process generating the network. We want to succinctly capture higher dimensional properties of the network. That is something other than an index that we could capture much better with a histogram, right? And it needs to be worth the space, whatever you're describing. If a picture should be worth 1,000 words, you've got to decide if you want to give up 1,000 words of your text to put the picture in there, right? And it should be compelling as best you can. And those are artistic elements. From a scientific side, we want to have the ability to replicate results. So scientific work should be replicable. Most of the features you see evident in a visualization should be quantifiable, right? There should be some extent to which you can map it on to a measurable quantity that has meaning in the actual setting. And it should be theory relevant, right? So it gives us something new to think about or put into our understanding of the process at hand. And we're actually really good at that in some things, right? So this is a classic example. Imagine I give you these 3 series, right? So if I give you an x-axis and a series of different y-axes and I fit a regression to it, I can tell you exactly what that is, right? So that regression, it turns out that this regression equation fits all 3 of those series perfectly. And you might think that that positive correlation is generating something that looks like this. But it turns out, of course, that that scatter plot could fit just as well as does this one. All 3 of these scatter plots have the exact same numerical summary down to the same means, the same regression coefficients, and so forth. And so this highlights why we care about visualization. Visualization lets you see the global features in ways that any kind of really highly accurate index does not, right? Because an index has to take a single dimension simultaneously and make it work, right? So I have to find out what's the slope between this. Well, the slope is going to be the same in all time pieces, but the slope is actually a function of multiple things, and we care about the data generating process more than just the slope itself. And so we want to make sure that we're getting at the more holistic side of this. Now, one question you might ask yourself is, why is this such an effective treatment of this problem? It's because we understand what a scatter plot looks like, right? So imagine I give you this scatter plot again. The reason I know what story I'm telling with that regression line is because I understand the relationship between the x-axis and the y-axis. I could instead represent this data like this, right? So this is the exact same data, and its data fidelity is high, right? I've just randomly reordered the x-axis. I would never do that. That's a ridiculous thing to do, right? But I could, right? There's nothing wrong with that per se in the sense that I could easily recover the data by going through and saying, well, the 0 points here and so forth. But it's silly. And the reason we don't do it is because we know intuitively that there's an ordering, and that ordering creates a relationship between the two that gives us this correspondence of slope and rise over run and so forth. The problem with network analysis is that we don't have that kind of a basic intuition space. We don't have an x and y axis that we can put things in. And so this, for example, are 3 published versions of the exact same data. These are the Karate Club data. And this is how it was originally published in Zachary's dissertation. A circle plot is useless, right? And these others are nearly as bad. And so what you'd like to do is come up with something elegant like we've done for scatter plots, like the gapminder type of thing where you can build in these multiple layers, but do it in a way that represents network space in a way we like. So how might we do that? We want to, that's another way of saying this. All right. So the solutions we've come up to with for the main problems with network visualization is that there's no obviously consistent display frame. So we don't have an X and Y axes. There tends to be too much information, right? So we have attributes on the edges, on the nodes. We have relationships amongst them. And the magnitude or side of the network can often be difficult to play with. And so the solutions to this problem have been heuristic solutions, where people try to solve one of those problems or the other. So we might want to have an even node distribution across the space. We might want to have consistent edge links. We might want to minimize or maximize edge crossings or some such. And these things allow us to get a layout display which answers one of these problems or another. And the short answer for this talk today is that these tend to be trade-offs. If you can do one of these things, it often comes at the cost of something else. And so you want to find a way to minimize that. Now, the part of the problem with this is that if you just go to your favorite network analysis software and pull an off-the-shelf visualization, you can get widely different results. So these are all the exact same underlying data where you just go through one program and click the visualization button on the software. There tend to be a handful of basic visualization strategies. And so the two most common visualization strategies are tree-based strategies or force-directed space-based strategies. So in a tree-based layout, there's some meaning to the y-axis. And so this could be authority, it could be rank in the social system or something like this. And you retain whatever quantitative variable you want to plot on the y-axis. And the x-axis is used to minimize line crossings or identify communities or something like that. Now, if your data tend to be a hierarchy, this is the best way to display it, right? So you can see a tree from a root to the leaves quite nicely, and it allows you to see the branches it moves for. The other standard way to display a network is what's known as a force-directed or a space-based layout, where the goal is to mirror the edge distance in the network, 2 steps, with the screen distance. So the further I am in the network, the further I am in the display space. And if you have a hierarchy in this space, it's okay. I can see that this node has only outgoing ties and no incoming ties, so that's probably my root, and I could trace branches, but it's clearly not nearly as easy to see as this is. On the other hand, if your network looks like if you use a space-based layout and plot it as a tree, you tend to get a mess, right? So don't use the tree-type layouts when what you really have is a space-based problem. The thing that spring embedded or space-based layouts are good at is identifying clusters in the network, or identifying these clumpiness to the underlying social space. And I'll go through some examples of that in an example. Now, a third common way of displaying a network is to use some sort of fixed coordinates. This is a hospital exchange network, excuse me. And in this case, hospitals live in a real geography, so you can plot it in the geographic space. Now, if I were to use a basic spring embedder or other kind of force-directed layout, what you find here is that it distorts the space, right? And so there's some lack of fit between what you'd get from a spring-embedded layout versus a space-based layout. But the advantage of something like a map is your audience understands the frame of reference, right? And so that's a huge advantage. We know where Texas is, we know where Maine is, and so forth. Whereas here, I'd have to try to figure out, well, where's Dallas, right? Some fixed-based layouts are pretty miserable, right? So a circular-based layout can really be a pain in the neck. It doesn't do a whole lot to display the underlying distribution of distances in the network. But you can often combine a space-based layout with a circle layout to look at subgroups of the network. So here I've used a space-based layout to center each of these circles and then just put each group as a circle on top of it. This little fit statistic you're seeing down here at the bottom is the correlation between the geodesic matrix and the Euclidean distance matrix on the screen, right? So a really good network visualization should have a high fit in the space-based set. These are pretty, right? These are called chord diagrams. They're the network equivalent of pie charts. They're essentially useless. Avoid them at all costs, all right? I don't know how anybody sees anything with these things. These types of networks are beautiful, and remember the advantage of a world map or other kind of spatial visualization is it gives you an audience frame of reference, but this sort of scale, really what you're getting is population density, right? So make sure that what you're getting out of something like a map is something that you need to get a map for. So in this case, for example, the reason we wanted to use a map was we wanted to highlight the fact that even though a patient might get admitted in Dallas, they're only 2 steps away from Chicago, New York, or Colorado. All right, so let's think a little bit more about what some of these kinds of layouts actually do, right? So when you're using a spring embedded layout, the reason we call it spring embedded is you imagine there's a spring between every pair of nodes in the network, and what the algorithm is trying to do is minimize the energy in that system. So there's a spring pulling these nodes together and pushing these nodes apart, and so this node's not connected to the other, so all of those nodes are pushing it away. And there's some balance then between the connections that are pulling you together and the connections that are pulling you apart within this 2-dimensional distinction, or this 2-dimensional constraint. And this is the overall balance of forces that would highlight that kind of connection. And when you have lots of ties bringing you together, that creates a knot that pulls people together, and spaces between pushes them apart. Now in this case, the highest fidelity fit to the data is given by letting each of these edges have equal weight. The problem is, in this case, there's one community here, there's another community here, there's another community here, and this pink community is kind of overlapping. And that's one of the problems you often get when there's a 2-dimensional representation of a high-dimensional space. And so you might want to highlight the group structure by increasing the weight of within-group ties and weakening the weight of between-group ties. And so by doing that, I end up with a smaller, sort of tighter-knit group amongst the green, amongst these communities, and you can see this pink group popping out a little better. Right? When you have these really dense knots, you can often go in and sort of blow it up a little bit. This is known as a fisheye distribution. Right? So here's the original space-based set. I want to go into the middle of this and open this up a little bit. And I can do that by literally taking the space and putting the fisheye lens over one part or the other. There's some questions about whether you want to display circles or edges as straight lines or curves. This is the classic element of what's known of the Gephi program, is they use a curved edge. I find curves a little distracting, but it's kind of a matter of taste. And if it's done really well on a sparse graph, it can be beautiful, but it doesn't provide any information. So it tends to be a chart junk feature. In Gephi, to be fair, there is an information content. This is the curve is turned to the left following the out degree. So this is a node from here to here, from here to here. Right? You might decide that you want to use multiple dimensions. So if the problem is this construction of fitting a node on one set, so why not use 3D? If you can get in and play with it, it can often be, you might be able to see something that's interesting. But by and large, the problem with 3D is that it's occlusion. There are things behind it. And so whenever you put it in a print set or you put it on the screen, you can't see it quite well. I find that small multiples can often be useful for understanding a distribution of networks, for example. So this was a paper we did looking at disease transmissions across different types of networks. And some of these networks were really sparse, and some of these networks were really dense. And this was a way to try to display what these different kinds of things look like. And then we were able to go through and say, well, what does it look like to really look deeply into the core of one of these bits versus one of the others? And so then you might say, well, look, what you really do have here when you get to this dense network is this highly connected ball that's hard to see. Now, the advantage of doing 3D when you can move it is you'll notice I put a little solid different colored knot there just so you can help the eye track where these things are moving from because they're hard to see. What do I have here? This is a point made earlier. I tend to try to reinforce elements as best we can. So in this case, I've colored the nodes by their degree. I've colored them by their centrality, and I've sized them by their degree, and those things are highly correlated. And so then you get this reinforcement of nodes in the middle versus the periphery that are mapped by both the colors and the size. One thing to keep in mind in something like this is that the default settings for most network analysis programs have the edges really thick. So if you make the edges small, if you make the colors move from some sort of a natural palette, and here it's sort of an autumnal palette from orange to green, that's a little more pleasing for people to see than the default sort of red and blue kinds of things. There are a lot of new ways of looking at networks interactively, and so let's see if I can get this to work. Let's start with Kieran's here. Going to let me out. Yeah. So this is these kind of networks are fun to play with. These are all philosophers over a series of bits. And what's nice about these is you can hover over them and see bits, but you can drag them and play with them. And so if you want to get in and lose a few hours of your day, you can go in with these kind of networks and try to make sense of them, drag them around and play with them. There's another fun one here. It's actually a great way to get, if you want some intuition about how a spring embedded layout works, use one of these examples, and you can just see, well, this thing's a little tangled up there. If I just jiggle it a little bit, it opens up, right? And so that's literally how it, like in this example, you can really see sort of the rubber band stretchiness. That's the spring that we're talking about, and it sort of snaps back and bounces. And this layout is what we're trying to do. But the nice thing about the interactive is you can click on things and figure out what you're highlighting. And so if you're trying to explain things to people, it's really nice. And for those of us in the room that would really like to convince ourselves that all the conspiracy theories we think about Trump are true, I highly recommend this website, which will take a moment to load. But this is an interactive graph of all of Trump's connections and business ties in the world. And it goes on forever, and you can link through and convince yourself that the end of the world is in fact nigh. So I'll leave that to the slides for those of you who want to play with it. Yeah, it's not going to let me respond here. Maybe there it's coming up. Yeah, but you can get in here and just do anything you want and see what's there. What's kind of nice is that this is actually a pretty clever visualization, because if you zoom in, you'll see not only what each person is, but if you look on the highlight on the edges, you can see what kind of tie it is. It's an ownership tie or something like that. So visualizations, interactive visualizations are great if you have an audience that's really interested in interacting with it, right? And so that's the main element of doing that. So there's if your networks are dynamic, we can use network movies. The idea with the dynamic network is that you have to decide whether or not you have miniature time slots versus the connections. I don't have the movie link on this. It's not embedded the way I thought it was, so that's not there. The problem with the beauty of movies is you can really see what will happen is this image will dance around, and there's some nice things about it. It's a great way to get a sense of the tempo of a social setting, so how interactions are sort of unfolding in real time. The hard part about movies is that people have a pretty poor visual memory for movement on the screen. And so it's great for helping you build some intuition and sort of see some patterns and then go in and look at it. But if you're going to display something or try to so it's great for interactive data. It's less used for your own understanding. It's less useful for conveying a point to an audience. For that, I prefer these kinds of small multiples where we can say this is what happens at time 10, at time 20, or time 30, and you can use those multiples to explain to people what's there. Now, another trick that is quite useful, especially for large networks, are to move from some kind of exact point in line representation instead to some kind of an abstraction of the underlying data. So imagine we wanted to look at a kinship network, right? So I have ego's father's, mother's, brother, sister, right? So this is the classic elements of kinship. If I go up the father's line, I can go my father's father would be my grandfather, my grandmother, my aunt, my father's brother's my aunt, my father's sister's my uncle, my aunt, excuse me. And so you can go through each of these elements and identify the entire set of multiple kinships, and I could do this multiple times. Or you could represent the entire thing as a grammar of social relations, right? So from ego's point of view, my father's 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 father would be my grandfather, my great-grandfather, my great-great-grandfather. My aunt would be my father's sister. My great-aunt would be my father's sister's father's sister, right? And so you can imagine going through this set and figuring out each piece. For this kind of a logic of a social system to work, there has to be some constraints on the underlying network. So not everything is connected to everything else. In this case, husbands can have fathers, but fathers can't have husbands. Right? And that's a gender constraint in a world where they don't allow same-sex marriage. Right? If you do allow same-sex marriage, then fathers could have husbands. Right? But you can imagine going through the social network to think about this kind of abstraction. And this type of abstraction is nice when the rules of the systems are really clear. Most social networks aren't so clear. So when you get a giant network where it's really hard to see the scale, you want to do something else to help to generate clarity on top of the network. This is a network of social science journals. So each node is a journal. Each tie is a link to whether or not those journals are essentially working on similar topics. And you can layer over this then a contour map. And a contour map lets you see the kinds of fields that are closely tied to each other. And by looking at the contours, you get a sense of what types of elements pop out. And because these are journals, this maps disciplines, right? So here you have economics and law down one side, political science up here, elements that deal with the mind, with the psychology, education, and so forth. Management is the link between economics and the mind, and the worlds and meanings over here in anthropology and so forth. And sociology fits right in the middle. This hasn't changed much over time. This is sort of a difference of about 6 years. Economics and law continue to grow. Chemistry is even bigger. The nice thing about once you get this rubric in mind, you don't need to have the nodes and lines at all. So this is a representation of close to 20,000 journals, if I remember correctly. And what's nice is that chemistry creates this bridge between the medical world, right, and the physical science world. And the physicists and the mathematicians who sort of think they're the center of the universe, in fact, are off on this one side, and I kind of like that. I tease Peter about this all the time. You can zoom in to other things, right? So this is a representation of the literature about network ecology. And so again, it's a bunch of journals, but we've just thrown away the nodes and lines entirely because what we care about are these clusters, and we can then label these cluster topics. This is all scholarship at Duke with that same kind of model, right? So it's a way of looking at that. We've done it similarly with these large-scale networks by getting rid of the points and just looking at the lines. And so we just color the edges. But if you make each edge really highly transparent, you end up seeing that what would normally look like a big hairball, you can see the clusters pop out in these different colors because there's enough of these really thin and transparent lines to create something that's opaque. And so that kind of a layering allows you to see something that you might not see otherwise. The other thing you can do is move from a point and line network entirely. So this is the co-voting network that Peter showed this morning. And you can do something called a heat map. And heat maps are great if there's some obvious way of ordering the axes. And what that allows you to do is see all relations simultaneously between each row and column of the adjacency matrix. And if there's structure to this, that tells you something that's often hard to see in the underlying network. The other way you could do it is you could define a process on the network and visualize that. So if what I really care about is understanding diffusion, instead of showing the network as a whole, I might instead say how quickly were different people in the network likely to receive the information. This is from Katz and Coleman's work on the diffusion of tetracycline. They just asked how quickly people were to receive information or to adopt this medicine, given how often they received nominations for being central in the network. You could instead do this as a distribution across all possible paths in the network, right? So I can imagine seeding an infection at each node and say this is the people that go out 1 step, 2 steps, and 3 steps. And this gives you a representation of the distribution of possible diffusion paths within this underlying network. And so in some places, I would start this network, and it would take forever for the population to get reached, whereas in others, I could start and I'd move quickly. But on the whole, you get this kind of a path. That would be the diffusion risk in this network. So if your goal is to try to understand diffusion risk per se, then focus on diffusion plots or something like that. We tried to play with something like this with color. It doesn't work particularly well, right? So if you imagine this was the source node, and so those are going to be in green and go otherwise out, you might be able to squint and see that this goes from green here to red here, but it's really hard to see. Instead, what we like to do is find some way to really focus in on the elements that matter within the setting. And so this was a disease simulation we did. And what we tried to do to communicate how this works was say, well, this is what the network looks like on a single day. And so this is a dynamic churning network. And what you see on any given day, there might be a few people that have a large number of relations, but most people have 1 or 2 ties in this set. But if you accumulate it over time, then you see lots of transmission in this network. And so in this network, it was a question about the differences between blacks and whites in sexually transmitted diseases. And so we have a homophily on race in this network. The simplest way to show a transmission network, though, again, is to start with your sources and move through your outcomes. And so this is work that Jake put together with, this is a different piece. This is another one. But anyway, the idea is you start with a seed node in the simulation. And here we've colored the nodes, the edges, if they're a concurrent relationship, if they overlap in time. And what's interesting in this case is that we can also color these by whether or not the continuation of the tree depended on a concurrent tie. And you can see that in this case, you might have some moments of non-concurrency in the graph, but you could never have gotten to these points out here if it weren't for concurrency somewhere upstream. And so it's a nice way to highlight where the concurrency happens. And then we might say, well, this is sort of selecting on the dependent variable, this is where the transmission actually happened in these simulations given our seeds. These are the non-transmission edges amongst the seeds. So you can see that it didn't happen everywhere. There were some places where there was transmission and some places where there not. We tried at one point to link these two things, right? So could we make it so that it's not just a transmission tree, but so we have the trees embedded in 3D on top of the spatial layout? It's cute. I'm not convinced that it works. But this is the spatial layout, and then it goes to the tree on the other side. An example of movement that I do think tends to be pretty effective is ghosting out relations if they occur, if they start in the end. So this is the sexual network from Ad Health again, and here we've just created a flip book where it's on at each given week. So this was a relationship that's ongoing, this relationship ended, and you can see this network emerge over time as the relationships keep going. Now, it's not that there was a big dating frenzy that happened right then. The issue is that we said relationships ongoing in the last 6 months, and those first ones you saw were just ones that occurred early in the set and were still ongoing. So this visualization is giving a little bit of preference to long-term relationships that are still ongoing or have been ongoing within the last 6 months of the interview. And as you'll see in a minute, it's not that they all died at the same time, it's that the data is right censored, right? So we just didn't have, we had to stop collecting data. But this is actually the visualization that prompted us to come up with our avoidance of 4 cycles rule, because you never see a timing where there are some 4 cycles in the collapse graph. At any moment in time, you never see them. So that's that. So another way to represent dynamic networks is to think about displaying them as temporal panels. And so in this case, a relationship between A and B starts at time 2 and ends at time 5. We can represent that as a relationship between A and B that starts at time 2, 3, 4, and 5, right? And it turns out then that B has a concurrent relationship with C that started at some point. So let's see, B's relationship must have started at time 3 and goes to time 7. And you can see that they overlap here. This works great for networks that are relatively small. You would need other kinds of ways of visualizing these if you have more panels than that. So here's the same way of doing it. Oh, come on. That's too bad. So this is a 3D version where we've just taken each panel and we've linked each person to themselves by an identity arc. And then you can, by using the 3D layout, it actually creates an alignment between the waves, which is kind of nice. The final solution to sort of the problem of too much density is that an idea that Peter hinted at before, which is that you can move, instead of having this kind of really dense hairball of Democrats and Republicans and a few people in between, instead we can identify structural equivalents in the network, collapse those structurally equivalent nodes to a single node, and then plot them together that way. And so here we just call these party loyalists at one point in time and another, and that allows us to get to this kind of visualization that we showed earlier in the day. And so once you have that, you can then pretty it up in various and sundry ways. But the key was, by throwing away a lot of information, you gain more insight. And that's a key element that often happens. What's left to be done in this field? One of the main things to do, I think, is something that Moreno started with, which was Moreno really tried to develop a grammar of visual graphics for networks. And so each of these types of elements had a meaning. And that meaning he tried to be consistent with over time, right? So circles were girls, triangles were boys, red was positive, black was negative. And by using this kind of visual language, his thinking was that we'd be able to see something and learn how to write a paragraph, if you will, with this language in a way that is harder to do otherwise. That hasn't really caught on. There's been some attempts at it. This is some different types of stylized block models that folks have tried to generalize by using different types of arrows, but it's again not caught on. It seems like thinking about this kind of thing would be useful. There's a distinction between thinking, again, style is always an evident feature of these types of things, and so it would be nice to distinguish between something like this versus something like that. Like, those are the two exact same graphs. The difference is this is what the machine gives you by default, and I don't know why this is not working here. This is what you get with a little bit of extra work. And that extra work you tend to have to do by hand in something like Illustrator or something like that. All right, so That's the end of the presentation element of this. I have a bit of examples to go through in terms of software and things like this. Questions or thoughts or comments before we go on to that? Just about strategies? Please.
What about when you have lots of networks that are changing over time?
What do you do when you have too much data to see at once? Right. One thing we've done is we've done panels of types of networks. So for example, if in that missing data paper that I talked about yesterday, we took 12 different networks that are representative of populations of networks and then create a panel in the same style of saying, well, this is the least dense, this is the most dense, and here's how they change, right? And so ideally with something like your camps, you'd have something that stratifies them. So let's imagine I have centrality in one case and the extent to which females are allowed in the other, and that creates a space of networks, and you can arrange them and say, you don't need to represent all 60 of them, pick archetypes from, say, 6 different elements of that set and display those and let other people know what they're at. That would be my recommendation. But the beauty of online networks now is you can create links to these visualizations and have them and say, here are 6 archetypical sets, and here are the other 45 that I wasn't able to show you, right? Other questions or thoughts? Please. Mm-hmm.
I think we have the ad help data set, which also have sample space. Is that
Right.
something that gets incorporated?
No, there's very little about, so the question was the weighting. When I'm speaking of weighting, I'm speaking of edge weights, so whether or not it's a strong tie or a weak tie, for example. If you want to use sample weights, so if each node in your, remember the assumption of these pieces, of these types of visualizations are that we have the population, so the sample weights would be irrelevant. If you wanted to imagine sample weights, what you can do, if you have one of these contour type sociograms where you have a surface over the top, you can put more or less weight on one node or another in the generation of that surface, and so that would let you do a little bit of that. I'd have to think really hard about whether or not that's going to accurately represent, the relations, because you would also want to change the underlying architecture of that node. Right? Please.
I have a network and I have placed the node in a map to show the distance between the nodes, but I am concerned with the protection of if people can identify which venue is that, because I am using venues that where people have sex and
Right.
so I am concerned that people can identify, oh look, this is the bar X. So how can I deal with that?
So the question was, so the point was that he has data on a map and would like to put the network over the map, but the concern is that's going to reveal the venues where things are happening, which is disclosing information that people might want, right? So I think that's or that you might be trying to keep confidential. Is that fair restatement of the question? Yeah, so I think that there your best choice is to aggregate up to some level that's of detail that gives the flavor of the geographic distribution without giving the exact location. So for example, you might use census blocks or census block groups as opposed to an actual address so that you're not getting at that kind of level of detail. And it's just going to depend on the context whether or not that's enough obfuscation or not. One of the things we've done with Ad Health, for example, is we've used the geocoded data, but we've transformed it from being in Cartesian coordinates to some other kind of a twist. So we've put it on a sphere, or we've we've flipped the axes. Like we've taken what was originally north-south and made that east-west. And the idea is just to make it harder for someone to look at the map and say, oh, I know that's, Troy, Montana or something, because they might know what it is. If you flip it around a little bit or transpose it, they're not going to understand what it is, right? So it depends on what you're trying to get at. If you really want your audience to know that this is Texas and that's Oklahoma, then you need to use the real coordinates. If what you want them to know is these people are near each other in social space, but I don't care about north and south, east and west, then throw that part of the information away. All right, let's take 5 minutes and stand up, shake the cobwebs off, and we're going to come back and look at some software for visualizing data.